Okay, cool. So welcome to Marin Software's first ever meetup. We think this is an exciting event for us. We're really excited to hear about Velox. And we hope to have a lot of other meetups in the future. So please give us feedback on stuff we screwed up or how we can improve. My email address is there. You can also message me on MeetUp. And what is Marin Software? So we provide a platform for managing, optimizing, and reporting on search, display, and social ads. And for Velox, the keyword here is optimizing. So this might seem simple, but the challenge is optimizing at scale. And so for that, we've decided to use Spark. We currently have a platform using Hadoop. We use Pig primarily, but we are now investing heavily in Spark. And what we do is we model ads and users to determine optimal bids based on business goals. Just to give you an idea about the scale, we bid on about 100 million ads every day. We have about 300 million click events per day that we want to use to influence how we bid. And now we've just hit a new milestone with our real-time bidding where we get 100,000 bid requests per second. For those bid requests, we get the request. Within 100 milliseconds, we have to evaluate how much we want to pay and then let the ad server know if we want to bid on the ad or not. So the key here is how we manage and update models at scale. And with that, I'd like to turn it over to Daniel, and he'll tell us about Velox.
Ryan, before you begin, maybe we could do a compaction of the audience. There are lots of people standing around, so I'd like a seat that don't want to step over all of the guests together.
Yeah, by all means, please come up. There's plenty of seats.
I'll do that. All right, Jack.
Okay. Do I need to unmute? I'll do it. Okay, cool. Great. All right, I'm just going to see for your physical. Yeah. All right, let's go.
There's still some open seats. This is loud. All right, cool. Thank you all for coming. I'm happy to be the inaugural speaker, I guess. So my name is Dan Crankshaw. I'm a second-year grad student in the UC Berkeley AMPLab. And I'm going to tell you about the system that I've been working on called Velox, which is, so I've given this talk before, and when I talk to people about it, I've been trying out sort of different elevator pitches, and the latest one that I've been on is that Velox is sort of a system to help you deploy and maintain machine learning models, which is not the sexiest pitch in the world, but hopefully I'll convince you that this is interesting.
It's sexy to us.
Perfect. I'm in the right audience then. So I generally encourage people to ask me questions during this, but I will say that the way this talk is structured, you're going to have questions in the middle of it that I'm going to answer a little bit later. So if you have a really burning question, I'm happy to answer it, but if it's not super burning, I'm going to ask you to save it for the end. I think we're going to have plenty of time. So before I get started telling you about Velox, I want to tell you a little bit about sort of my background and where I'm coming from and this AMPLab thing. So AMPLab, probably in Silicon Valley, is right now most well known for Spark. But the lab is this sort of interesting Berkeley creation. So it's a lab in the computer science department at Berkeley. And we've been doing these labs for about at least 15 years or so. And the idea here is that a bunch of professors in sort of different areas of computer science get together, and they put together this 5-year lab, they get a bunch of funding, and they tackle some big, hard vision with the idea that by having this cross-disciplinary, having all these grad students sit together and talk about these problems from their different perspectives, that maybe we can solve hard problems that people sitting in different rooms across the building might not be able to get to. So the AMPLab is the latest one, or one of the latest ones. So AMP stands for Algorithms, Machines, and People. And I took this quote from our website today. Basically, the goal of this lab is to develop new tools and new techniques to help you answer deep questions over dirty and heterogeneous data. So we're trying to sort of push this idea of what you can do with big data even further with a new generation of tools. And we're doing that by combining algorithms, mostly in the form of machine learning. So we have faculty members like Michael Jordan as part of the lab. Machines through this abundance of cluster compute resources and all these elastic compute resources. And people through both crowdsourcing systems and experts. There's some things that people are still just the best at. We want to combine all of these things to tackle this challenge. So we've had a lot of success, we think. We've developed systems like Spark, as well as systems like Apache Mesos and Tachyon, and then some of these systems that are built on top of Spark that really add a lot to the power of Spark by itself. So things like GraphX for large-scale graph processing, ML-Base for machine learning, BlinkDB for exploratory data analysis. And together we refer to this as the Berkeley Data Analytics Stack, or affectionately BADAS. And it's this collection of tools that are all sort of designed with each other in mind, designed to work together, some better than others. It's, ultimately we're doing research and we're trying to push the research as well. But we really do have a focus on open source, useful software. So we've got this BADAS stack. People are starting to use it. But we're not done yet. The lab still has a few years of life left, and we certainly haven't sort of solved big data. And so Velox is, the goal here is to fill in one of these missing pieces. Namely, what you do with a machine learning application or machine learning model once you've used Spark to train it. So I want to first, with an example, sort of convince you that this is a problem right now, and a problem that people are really struggling with, and then I'm going to tell you how Velox is going to help you with it. So as an example, let's say that I want to build Catify, so a streaming music service for cats. And I wanted to use the BADAS stack, and I want to use machine learning to provide the best possible user experience. So I want to use machine learning because I don't want to just play random songs for my cats, I want to play the best songs. Well, if I want to use machine learning, the first thing I need to do is figure out what am I actually trying to predict? What am I modeling here? So in this case, we have sort of a recommender system. So I have a bunch of users in my system, and for every user, for every cat, I have all these songs in my catalog that I could play, but I have 20 million of them. And what I want to be able to do is figure out, I want to be able to predict, for all the songs that my cat hasn't listened to yet, had she listened to them and rated them, what would she rate them? And if I can predict this with some accuracy, then I can take these unheard songs that have the highest predicted rating and play them for her. She's going to be really happy. So to do this, using BADAS, I'm going to start with some training data set. So some existing ratings. I need something to build my model off of. And the idea here is that I have existing ratings, so I know what some of my cats think about some of my songs. And I'm going to use that information and build a statistical model to help me extrapolate what the rest of my cats think about the rest of the songs that they haven't rated yet. So to do that, I can feed it into Spark, and I can train a model in Spark. And generally the result of that is something that's sitting in Tachyon or HDFS or something. But it's just sort of sitting there. And it's probably some, if it's a model, it's probably some parameters that Spark understands. They have semantic meaning to Spark, but ultimately it's just bytes on disk. And if I want to use that model to actually serve my cats the right songs, well, I need some way to serve cats songs. So I'm going to put up a little web serving tier. And this gives me a way to serve songs to cats through my web interface. But now I have this problem where I can serve songs, and I have a model that tells me which songs to serve, but they're decoupled. They don't know how to talk to each other. And that's sort of the core problem here. I have this model that has semantic meaning to Spark. It's going to tell me exactly what songs to serve to all my cats. But I have my serving tier that can serve songs with really low latency, so my cats can get them as soon as they want. But they don't know, it doesn't know which songs to serve. So what we need to do is figure out a way to get the model trained in Spark into my serving system. So one way, which is sort of a straw man, but I've actually talked to people who do this, is for a recommender system, I can take all of my users and all of my items, my songs in this case, and pre-compute all of the predictions. So I can pre-compute this cross product. And now I've taken my model that Spark understands and turned it just into data that any sort of database can understand. I now have predictions that are keyed on user and on song, and maybe I can do some filtering to just throw out the bottom K or pick the top K. And And now I can put this into MySQL. And this gives me a way to get my model from my analytics system, my training system, into my serving system. So now what this sort of looks like, what Catify looks like, is I take my training data, I train a model in Spark, I write it to HDFS, or maybe I use Spark directly, and I pre-compute all of these ratings. Then I pipe these ratings into MySQL, and now I can serve predictions. I can serve songs, I can serve the right songs, and my cats are really happy for now. And this actually would be like not a bad solution if the world was static and nothing ever changed, but as I'm sure I don't need to convince anyone here, that's not the case. And so what we have is this ratings black box that MySQL understands. And as my cats are interacting with the system, they're generating new training data, they're listening to new songs, they're rating new songs, they might even be like having changing user preferences. So they might have liked Rihanna yesterday, and now they're on a Taylor Swift binge. And I want to be able to incorporate that, because if they liked Rihanna yesterday but not today, then I don't want to play the Rihanna. So I want to take that training data and use it to update my model. So I can do that. I can take my cats interacting with the system, take that training data, put it into Spark, retrain a new model, pre-compute this black box, stick it back into MySQL. This all works okay, except it takes a long time. There's like a high latency loop. And the problem here is that MySQL doesn't understand this black box, and Spark can't train. So that's sort of the thesis of why we need a system like Velox. We have this serving system that knows how to serve low latency predictions, but it can serve stale predictions because it can't incorporate new training data into this black box that it's serving. And we have a batch training system that can maybe do some incremental maintenance, but it's hard when we have a bunch of different models at once that we're trying to incrementally maintain. And it certainly can't serve. And the result of this is we have what we've been calling ad hoc model management. I've actually looked at some systems that sort of claim to do this model serving, and they literally, like quoting from their documentation, say the best way to get your model from Spark into our serving system is rsync and a cron job. Like we can do better. So Velox ultimately is focused on providing both low latency and fresh predictions. That's what brings value to your customers. That's what provides the best user experience. That's what maximizes your customers' revenue, is low latency and accurate predictions. And we're going to do that by breaking this abstraction of a model, breaking this black box, and looking at building a system that understands how these models work. We're going to do model-specific optimizations both on the serving side, on the training side, on the maintenance side. And we're going to do all of it in a single system to ease the operational pain of deploying machine learning-backed applications. So if we take another look at this badass stack, and we look at it in the context of deploying and building these machine learning applications, we have a bunch of systems that are really good at training models. They're good for other things as well, but in the context of machine learning, they basically sort of all fit in the training umbrella. And what we need is a system to complement all of that, to do management and serving. And so that's what Velox does, is it complements the batch training, the heavy lifting that Spark can do, by having a serving system that understands the semantics of these models and can do something about that. So there's two components to Velox. We have this model manager, which is responsible for keeping the predictions fresh. And we have this prediction service that's responsible for providing the predictions to the end user with low latency. So I'm going to dig into each of these a little bit. But before I do, I want to give you a little bit of a flavor of what it might actually look like to deploy Velox. So at a really high level, Velox is a standalone Scala service. People are really into services these days, according to my browsings of things like Hacker News. We do automatic integration with Spark. We're built on top of Tachyon right now, but it's actually a pluggable persistent storage backend. And the idea here is we provide personalized predictions as a service. And the reason we want to provide it as a service is because we want to make it as easy as possible to add a system like this to your existing front-end infrastructure without sort of changing anything that's already working. And it's deployed as a shared nothing serving cluster, a pretty standard setup. So to use it, say I have some front-end Node.js application that's serving my, my cat's songs. And now user 4 logs in. And I want to figure out what song do I play her. Well, my front-end application doesn't need to know how that decision is being made. We're going to defer that to Velox. So the front-end application is going to send a predict request through our REST API. Velox is going to compute what the right song to play is. Maybe that's computing the score, predicting the score. Maybe it's doing some top K to figure out what the best playlist is. But whatever it's doing, it's going to return a score, and the front-end application can just go and play that song. It doesn't have to worry about any of the sort of predictive component of our application. The next thing we want to do is we want to keep these models up to date. We want to reflect new information. So in our Catify example, when Cat4 has listened to that song and now rates it, the front-end system can send that new training data, that new information, back to Velox. And Velox can update that user's model in real time. Remember, we're doing personalized predictions, so we're going to have some differentiation of our predictions between users. And then finally, we're still doing some of the heavy lifting in Spark. And I'll talk a little bit about what actually gets trained in Spark versus in Velox. But there are some parts that we defer to Spark. We don't want to throw away all the goodness of the badass stack. There's still a lot of batch computation that needs to be done. And so when Velox decides that some of the models need to be retrained in Spark, we send a batch train RPC to Spark. We just execute the same Spark programs that you guys already know how to write. And when that's done, the new model gets sent to all the Velox servers, and we update to the new model sort of transparently. So now I want to talk about what each of these three components sort of does. And I'm going to start with the prediction service. So our prediction API is really simple right now. There's basically two components. So the first is you can ask for predictions that look like, for this user and this item, predict a score. And then for recommender systems, we also expose a slightly more complex ordering query, which is useful when you're trying to generate top K lists, like playlists. And this says, for this user, give me the top K items. I don't really care about their scores. Now these are all personalized predictions. I'll talk about what personalization buys us in a little bit. And because we're building sort of knowledge of how these models work directly into Velox, we can do some intelligent caching, looking at partial reuse of different pieces of the model, and so that we can serve these predictions with really low latency. So when a prediction comes in through our REST API, it gets translated to this Scala method call. And we basically have to do two things. First, we're going to look up that user's model. We have a different model for each user in our system. But because every request is associated with a specific user, we can treat the user ID as primary key for this. And so we can shard both our queries and our data by this primary key, so this user lookup is always local. The next thing we have to do is we have to compute the features of the input. Now, this feature computation could be somewhat expensive. And the reason we're doing this featurization, for those of you who have less of a machine learning background, is that sort of like the raw input to a song, for a song, it's not even clear like what that should be. Is it the album art? Is it the raw sound file? That's not so useful. So what we do is we basically figure out a way to quantify these things, these inputs, into their defining characteristics in some sense. And then we train a model on these defining characteristics, which we call features. And that's often really domain specific, and sometimes can be really expensive. For a recommender system, maybe it's just a lookup of the latent factor models. But for like an image processing pipeline, we might be doing a bunch of processing of the image, or if we're doing sound recognition, it might be more expensive. But the features are independent of any specific user, because the features of Taylor Swift are going to be the same whether you're making a prediction for you or for me. And so we can cache this and reuse this computation and amortize it across all the users. And that's basically point predictions, not super complicated. To add this top K component, we take the really standard databases approach of the first thing we do is the user provides some sort of query predicate. That might be a playlist that we're trying to figure out the top K items within that playlist. It might be some keyword search. whatever it is, it's going to generate a candidate set. And then once we have this candidate set that is generally significantly smaller than the entire catalog, then we're going to exactly score and rank all the candidates in this and return the top K. This is a pretty common approach to how people are doing top K recommendations today. But I've heard it sort of expressed, people that have expressed interest in expanding the size of the candidate sets that they can support. One of the nice things about the way we've described the model in Velox, which I haven't told you yet, but I will tell you soon, I promise, is that we can actually use some recent theoretical work in the machine learning community, including the best paper at NIPS this past year, which was computing maximum inner products for linear models, which is sort of exactly this top K problem, and also some recent work in matrix compression to do this really fast and expand the size of the candidate sets that we can support, potentially even to the size of entire catalogs, like 20 million items. And that's basically how predictions work. Once Velox has computed a prediction, we return the score, and the front-end system can get on with its day. Now we're really focused on low latency predictions, so everything I've described we can do in my simple tests, roughly a millisecond, but sort of 10 millisecond SLAs are what we're aiming for. And we're pretty sure that we can hit that for a lot of different models. But some of the more interesting stuff in Velox is how we keep these models up to date, how we keep them fresh. And that's sort of all in the purview of the model manager. So I keep talking about personalized modeling. And I want to spend a second to talk about personalized modeling and sort of some of the, it's actually not as straightforward as, at least as I imagined until I started working on this stuff. So when I heard personalized modeling, sort of before I started working on this, I thought, let's do the naive approach. Let's train a different model for each user. Each user has some interaction history, some training data. Let's train a model on that. So we could do that, but it turns out that there are some problems here. So one of them is if we're thinking about users as literally users, people. I don't know how many of you religiously rate every song you listen to, every YouTube video you watch. I certainly don't. So there's this computational issue, which was sort of the one I thought of as a systems person, which is, okay, we have to train a bunch of models. But it turns out that there's also a statistical inefficiency issue, which is most users, there isn't like a lot of training data for any individual user. These user interactions are pretty sparse, and the problem there is that we end up overfitting our models, we don't get robust predictions, and it ends up not being very useful. And even though we have some personalized component, it might end up being even less useful than for getting out personalization at all. But luckily, the machine learning community has spent time thinking about this, and there are some solutions. And we're going to utilize that in Velox. So one way of thinking about a model is something that takes some input, and it's a function that takes some input and computes a rating. But as we're learning more and more, these models tend to be composed of many different steps. There's some featurization steps. There might be several models that are predicting different things. And we can treat each of these components of this pipeline sort of individually. So in Velox, what that translates to is we're going to split our model into two components. We're going to split our model from one model is going to compute the features, and the output of that is going to be a feature vector. And that's useful if we want to use things like an SVM to predict whether this, this input is in some category or not. And then once we've computed the features of our input with one model, we're going to feed that into a separate linear model, and that's going to compute the rating. And so how does this apply to personalization and alleviate this statistical inefficiency issue? Well, we're going to share these feature models. As I hinted at earlier, the features of an input are probably independent of a user, and so we can share these feature models. And so we're going to train these feature models on all of the training data across all of the users, and that's going to add statistical robustness to our predictions. Because we're training on all of the users, we have big data, and we have big data that changes slowly because any particular user's next interaction just isn't going to change things very much. And when we have a computation that has a lot of data and that changes slowly, we're going to use a batch system. We're going to use Spark. So we train these shared feature models in Spark. It's a really big computation. This is sort of probably what you're thinking about when you think about training a model in Spark. And then to supplement that, I mentioned that we feed the output of these features into a linear model. And we're going to have a separate per-user linear model, and that's going to add personalization here. So every model is going to take the same featureized input and compute a different score based on that user's interaction history. So because we have these personal models, they're only trained on a single user's training data. So we have small data. And we have small data that might change quickly because we want to be able to adapt to quickly changing user preferences. When a user downloads a song or skips a song really quickly, we want to be able to adapt to that and incorporate that information into the next recommendation that we provide. So because of that, we have small data, so we don't need the power of a batch system. And we can't really afford to be tied to the latency, the training latency of a batch system. So we're going to train these models online directly in Velox. So if we take a look at what that actually looks like, I like to have this in there because my audiences sort of have very different backgrounds with machine learning, and I know I sort of, the first several times I was presented with, lots of talk about features and models and stuff, I was like, okay, that sort of makes sense from an abstract standpoint, but like, how do I go write that code? So what that ends up looking like is we have an input, a song in Catify. We're going to first feed it into one function, our feature models, and the result of that is going to be a feature vector. It's going to be a vector of doubles. We're then going to provide that vector as input to our second function, our linear model, and the result of that is going to be a prediction. And then if we want to make a prediction for the same input but a different user, we can reuse this featureization component. This is what we cache. We feed it into a different user's model, and we get a different prediction. Now, from a mathematical standpoint, what that looks like is for some function x, or for some input x, so Taylor Swift's song in this case, we're going to compute our features of x, which is a function of both the input x and our model parameters theta. These are shared, they're changing slowly, trained in Spark. And then we're going to multiply that, we're going to compute the dot product with the per user model. Every user has their own W. This is what's personalized, and the result of that dot product is going to be a rating. That's our prediction. Okay, so that's a lot of talk about models and lots of lines going different places. Back to Velox, in order to drive this model training, we have this feedback API. And this is what happens when a user rates a new song. We want to be able to incorporate this new data into our model. So this feedback API is just a supplement to this training data that we started with. We started with existing user ratings, and this is just a way to provide another one. So this says for this user and this item, here's the ground truth score. We want to refine our predictions with this additional piece of data. So when we get this feedback, we do a few things. We do this online learning that I've been talking about. We're going to continuously update our user models in Velox. So when this feedback comes in, we're going to update user 22's model and not touch any of the others. We're also going to log it because this information might be useful for training our feature models as well. So that goes into Tachyon or whatever your persistent storage backend is to become available for offline training as well. And then finally, we're going to do some evaluation because when you have these things running in production and you're retraining your models, it's really important to be able to monitor how these predictions are performing. So this evaluation, right now, we're thinking about really simple things. But basically what I'm interested in here is we know what the monitoring dashboard looks like from a physical performance standpoint. And I want to figure out what the equivalent should be for a statistical performance standpoint. And we need feedback about how our models are doing in order to drive that. So what happens from a sort of a code standpoint is this feedback gets provided through our REST API. For online learning, it gets translated to this Scala method call. And here, basically, we have this linear user model. So we're going to update that model and write it to our persistent storage backend to be incorporated into making new predictions as soon as possible, on the order of 100 milliseconds or so right now. And because this is a linear model and it's trained on small data, we knew this really quickly using really standard techniques like stochastic gradient descent or some techniques in incremental linear algebra. And then to train the feature models, which doesn't need to happen as frequently, but our serving system is not going to try and do. We're going to use our batch system for that. We send this batch train RPC to Spark, and now you get the full power of Spark and all the existing work that's gone into training models in Spark with all the algorithms in ML-based and stuff to train your feature models. So we're looking here at using batch train in Spark. There's also some models that might be amenable to incremental updates of some sort, in which case we're also looking at using Spark streaming for that. And finally, we're looking at some automated retraining policies based on this evaluation that I just mentioned to figure out when we need to retrain and trying to get away from sort of a time-based system like retraining once a night. So sort of at a relatively high level, that's what Velox does and the problem it's trying to solve. But before I wrap up, I want to briefly mention sort of one additional problem that you run into when you start deploying these machine learning applications that are being retrained over and over again in these long-running applications. So the problem here is that we start with some training data, and we use that to train a model. Then using that model, we make predictions. We get feedback on those predictions, which becomes more training data. And we repeat this over and over again. And this can lead to some issues, particularly an issue called sample bias, where the training data for our model is influenced by the model itself, which can lead to self-reinforcing behavior. We can get stuck in sort of local optima rather than better exploring the feedback space, and our model can sort of stagnate. So what that translates to in Catify is I could always serve the best song. I could always serve Taylor Swift, but that's probably not the best thing to do. And there's actually a relatively famous paper about this where they ran into this issue in Yahoo News where the Yahoo News recommendation algorithm ended up just serving gossip articles because people click on those, and even though that's not necessarily what people like the best. So there's a solution here. It's this area of machine learning research called active learning. And a really, really simple example of that is this Epsilon greedy algorithm. And the way this works is with probability 1 minus epsilon for some small epsilon, we're going to serve Taylor Swift because we want to be able to exploit the model that we have to provide a good user experience. But with probability epsilon, so some small percentage of the time, we're just going to pick a random song to play. So while most of the time we'll play Taylor Swift, some of the time we'll play, I can't remember what band I picked, but some heavy metal band, Slayer. We'll play Slayer. And this way we'll continue to explore the feedback space and we'll try and avoid the sample bias problem. So this is epsilon greedy. And this works sort of okay in practice. It's better than nothing in a lot of cases, but it can actually lead to degraded user experiences, and there's some other issues here as well. But it's emblematic of this huge body of theoretical machine learning research called active learning that balances how to trade off this explore-exploit trade-off of exploring the feedback space and exploiting the model we already have in intelligent ways. So we're really excited about incorporating some of these techniques into Velox going forward. So to wrap up, I talked a lot about this Catify running example, and it sounds like you guys have sort of a setup that looks somewhat like a recommender system as well. But we're really hopeful that Velox is going to be useful for a lot of things besides just recommender systems. Personalized modeling has applications beyond recommender systems. So things like spam or anomaly detection can benefit a lot from personalized modeling because what's a fraudulent credit card transaction for me might be very different than for you or for you. And then there's also sort of applications where your entity, your user, isn't actually a person. So there's sort of a big buzz about IoT right now. I've yet to get a sort of a solid definition of what IoT actually is. But people are excited about it, and they're excited to give researchers money to work on it. And there's a lot of excitement about being able to incorporate machine learning into these devices that you have deployed everywhere, and be able to have a different model for every device that you have deployed. There's also sort of you can think of your entities as geographical regions. I talked to a power company that has a bunch of solar panel deployments, and they want to have sort of the same type of model, but a separate model for each deployment to model the weather better. And then hopefully I can talk to some of you about how you guys think about machine learning. And you know, I'm a systems person, so I like to build systems that have sort of these general abstractions that are applicable to a wide range of problems. So I'm definitely interested if you think that you could sort of squint and make your machine learning applications look like what I described. But I'm even more interested if you don't think you can, because I'm always looking to sort of figure out what the boundaries of these abstractions are and how we can push them. So with that, I'm going to wrap up. So Velox is this new piece of the badass stack. It's this missing piece that complements all of this training infrastructure that we have. And that's the serving component that has this semantic understanding of models and can serve them and keep them fresh. And we need that because today, model training and serving rely on ad hoc manual processes often. They're spread across multiple systems. We end up sort of cajoling systems that weren't really designed to be doing what we have them doing. And so we sort of get non-optimal performance from both a freshness perspective and a latency perspective. So to address that, Velox automatically maintains these models, provides low latency, fresh, and personalized predictions. And coming from the AMPLab, we have a strong commitment to open source. So Velox is going to be an alpha prototype release. It's going to be released soon. Sometime in May is what we're shooting for. And the hope is that going forward, this will be a new component of badass. In the meantime, we do have a project page. It has a link to our CIDR paper, which is sort of a vision paper that outlines sort of the initial infrastructure and some of the problems that we were thinking about when we came up with Velox, and you can find that on the page. And you can also send me an email. I'd love to talk with you further about that as well. I'm also going to be here I'm happy to stay here for as long as anyone wants to talk to me. So with that, thank you all very much, and I can take some group questions now.
So my question is the model, you talk about sharing the features, and that part was on Spark, right? And then you have the other piece. So we have I have two references. The deep learning, is that a similar to that kind of separation of the topic?
Yeah. So as far as I can tell, most people when they think about these models, they don't really think about sort of splitting them and training them in different places. People generally have sort of the place that they train models. Now, deep learning sort of fits into this. You can actually think of this as a deep learning neural network. So one of the things that people are really excited about with deep learning is that at least some of the hype is that you don't need to do this featurization process. That deep learning can sort of automatically learn that, and it's learning these features really, really well for certain domains. So you could just think of a deep learning pipeline as being your featurization process. And deep learning pipelines are sort of composed linear models. So you could just take the top layer of your neural network and treat that as a per-user model. That's sort of how I see this fitting into Velox today. That being said, I don't know if there's any evidence that that works well, so I'm not going to tell you to go ahead and do it. But in terms of sort of the system abstraction, I see deep learning as fitting in very naturally. Now, one thing with deep learning is that the actual making a prediction with these, multi-billion parameter deep learning models is actually computationally expensive, so we might have to do a little bit more work. There's been some good results using GPUs to not just train these models, but also to serve them. So we have to do a little bit more optimization work there.
I have a second question. So let's say you have a different, quote, deep learning type of algorithm, right? So you're not just neural network. You can have other bases, like radio basis function or something. Is how hard it fits to your Spark and Velox, this combination? Can I customize my own learning by use those, map reduce kind of, composition?
No, okay, that's a good question. it sort of depends what your model looks like, but basically we, when you implement a model in Velox, at least right now we have a very bare bones interface that you implement. And the things in there, or some of the things in there that you can specify are how to train it in Spark and provide these features. And then we're right now assuming that sort of all the personal models, all these models that Velox knows about are the same, these linear models, although we're exploring some alternatives there as well. But yeah, you can basically implement whatever model you want. And you can use all of Spark because training these feature models runs in Spark. Now, could you customize how the model is split between Spark and Velox is a good question, and one that I don't have a good answer to, but I'm really interested in. Yeah?
A couple of questions, details about some of the things that you said. When it's in the, when the user is interacting, it's interacting first with the Velox, and then that sends the batches to Tachyon.
Mm-hmm.
Okay, so how long is that data stored in Velox? And is it overwritten over time? Is it?
Yeah. Okay. So we're talking about like here.
There. Yeah.
Yeah. So okay. So what we do right now is we cache these user models. So you can think of Velox as a write-through cache to our persistent storage backend. So we have this persistent storage because I didn't want to deal with anything like fault tolerance for now. So it's sort of, there's always a user model cached in Velox right now. If you're asking this from sort of a privacy perspective, there are things we could do. And that's actually, so when we talk about personalized modeling, that's actually a really interesting and hard problem that I'm hoping to work on some more, a little bit in the future. But they're always cached in Velox.
My question was focused more on, is that data lost? You know, where you have a cache
Mm-hmm.
right there over a period of time based on some preferences and feedback and ratings, and then that sends the batch back. Is that data lost because, or is that's incorporated into the new model?
Oh,
but that
okay.
original cache, does that
So,
go away? If I ever wanted, for some reason, I was using this for something else, not Catify.
Sure.
Had some other purpose for this. But if I ever wanted to go back and retrieve at a certain point in time the cache.
Yeah. So we're doing, we're planning on doing versioning. So yeah, that's another good point. This is sort of me in my academic bubble, not thinking about these things too much. But yeah, we're planning on doing model versioning. Because data scientists tend to be really interested in this type of thing and seeing how these things evolve. So the plan right now is that when we update a user model, the old model will be written to some persistent storage with a version number.
Okay.
And so you can track the whole history, and same thing with the feature models as well.
And then when you were talking about the categories, when the arrows were going out and you were saying the categories, are those categories predefined or are they defined per your user?
Sorry, are you talking about?
You were saying it comes out in twos?
Talking about here?
Yeah.
Mm-hmm. And
so you had, there was 3 blue lines,
yeah.
2 blue lines, and then
right.
and so you were saying, you said those 2 blue lines that came out were the categories.
Okay, yeah, good. So this was just trying to illustrate, okay, so this was just trying to illustrate basically features being on or off. So the idea here is that these are maybe different pieces of your input. So in the case of songs, maybe that's the name of the song and some human tagged genre and artist information and maybe the sound file if you're doing sort of Pandora style music genome stuff as well. So this is just sort of input to a function. And that's going to be the same for all of your users, and that's sort of model specific, domain specific. That's something that your data scientist is going to come up with. And then which blue lines come out, that was sort of indicating often these features or these categories are sort of, they're binary, so it's either on or off. So it's like, this is an upbeat song or it's not. Or this is, a song that males between 20 and 40 like or not. And so that was just trying to indicate that feature like 0 and 2 are on and the middle one is off. And those are going to be the same for given input. And then the idea here is that we have a model. The user model has sort of a parameter associated with each feature. And so blue line goes into blue line. I'm not going to talk too more about that. To maybe make it clearer, I could use a whiteboard. But this is just sort of an illustration of a model being evaluated for specific input and 2 users. Does that make sense?
Basically predefined then.
Yes.
On or off.
It's part of the process of figuring out whether they're predefined or not, or on or off, is I'm not sure how to answer predefined. We can talk more offline.
But isn't that output of your feature extractor the whatever in Spark?
It's trained in Spark.
Right. So the output of that on and off features should be the output of Spark, right?
So no. So here, maybe this will be a little bit clearer. So this on and off feature stuff, this is a function. It's a function of your input, and it's a model, so it's a parameterized model. So what we do in Spark is we compute the parameters for this function. And that's this theta. And then we take theta, and we take the code that knows how to calculate this function. We put that in Velox. And then when a new input comes in, we evaluate that function.
Yeah, but the one that you showed before, the blue lines, you said on and off. It's on and off the new feature, right? Not the original feature. Is that should be this output of this blue box? Like when you say shared feature,
yeah.
Does that?
Shared feature means that this function is the same for all of the users. Right.
But does that has a physical meaning still? Does that mean still like your original feature? It's somehow it's like a factor analysis, right? So you kind of combine the original feature to something new, but this new thing may not have a physical meaning. That's you said it's on or off, but what is it? Is it? That's
domain specific, and basically when I have my data scientist who comes up with a model and they say this is going to be the best way to predict what my users are going to rate songs, they have some input.
So that's input feature. I'm asking the one that out of your first layer.
Right. Okay.
Yeah. So what that feature is that? That has a physical meaning.
That it may have a physical meaning. It may just be the output of some statistical process. It's really dependent on whoever's coming up with the model.
So maybe I can address that. Say in song, right, there are 100 attributes. Pandora had 100 attributes.
In the beginning.
Netflix has maybe 200 attributes for a movie. So that's the feature set of the input. But it changes with time. And that doesn't change on a day-to-day basis. Right.
My question is, that's fine. You have 100 features in 100 of input in the beginning. After your first layer, your feature function, that F, and you come up with maybe 10.
Okay.
What is that?
Okay, I see what you're saying. So this probably makes a little bit less sense in the context of a recommender system. Let's say that I had, a fraud detection system, okay? And the prediction I'm trying to make is this user swiped this credit card. So the input is some things about the credit card transaction, like where it happened and the time of day and how much money. So that's going to go in here. That's going to be the input here. And what we've done is we've trained a model in Spark across all of the fraudulent credit card transactions and non-fraudulent ones that we know about. And that model is going to say, it's going to extract some additional meaning from this combination of inputs. where the input is time of day and amount of money and location. So maybe we know that maybe we do some clustering, for example, and we know that high charge transactions that happen at 4 in the morning are often correlated with some behavior. And we don't know for a given user whether that behavior is fraudulent or not, because maybe I'm a teenager and I like to go spend a lot of money at 4 in the morning, but my neighbor is, a mother who has to wake up at 7 and never does that. So the feature is just going to say, this transaction is part of that cluster.
Yeah,
and then for each user, we're going to evaluate whether that cluster, being part of that cluster, is anomalous or not. Does that make sense?
Yeah.
But how?
Yeah, go ahead.
But how can you determine the intermediate features? Like for labels, we only have it at the last layer. We don't have the labels in the intermediate layer.
So that's once again model dependent. It turns out that there are a lot of people who are building models where they have some models that are themselves, or their featurization process are themselves models. Like in image processing, there's some clustering that goes on, for example. In the case of like a recommender system, these matrix factorization models, like when you hear about collaborative filtering and stuff, the result of that is exactly this. So we have, the result of that is sort of a per item model. Those are going to be the features. And a per user model. That's going to be the user model. So that sort of corresponds to this picture pretty clearly. There are definitely cases where your where you only need one layer and your featurization is not a model. I don't have a great sense for the trade-off of cases where people either want to or are sort of composing multiple models in a row, but I know that there are people who are doing it. Yeah.
If an organization had, say, 20 deployed models, 10 were written in the Spark stack, the Scala maybe, and 10 were in various other languages, machine learning libraries, and they sort of dreamed of having one service layer that could serve them all. Has there been any work done on Velox that would sort of allow plugging in of other
yes.
libraries?
And in fact, that's something that we're actively working on. So I talked about Spark because I'm from the lab, and there's a lot of, there's some advantages of integrating closely with Spark. We're hoping that we can do some code reuse and stuff, but there's absolutely no reason that the batch retrain function that you implement when you implement your model couldn't be pluggable. So one thing that we're looking at is using Wabbit, which is this really fast linear regression library, basically, that a lot of people are using. Basically, all Velox cares about is that there's some parts of the model that we can maintain really cheaply, or cheaply enough that we can do it. It makes sense to do it in a serving system. And there's other parts that you want some more heavy lifting power for. And we're working on Spark right now, but the plan is to be agnostic to that. Yeah.
Okay, so I have two questions. One is just like general scope of the project. Like, is it pretty much entirely meant to be for personalized models, or it'd be really nice to have like one service to serve all your models. Like, so for example, if I wanted to like train a model online and then pass the parameters to some sort of batch process and pass them back to an online model, is this project meant to do this sort of thing, or?
So that's a great question, and I want to talk to you more about that because I'm curious if you have something specific in mind. So we started with personalized model. So really what we did was we started with these generalized linear models, which is like what this is. And adding personalization basically gives us, so adding personalization is a convenient way to give us a model that decomposes into a piece that's trained in batch and a piece that you can train sort of more cheaply. So for that reason, we've been focusing on personalized models right now. I'm sort of actively looking for other ways to decompose a model into these sort of two computational domains. From a serving standpoint, there's no reason why we couldn't support a wide variety of models. The personalization component is sort of baked into my research prototype, but there's no reason for it to be, and that's like a matter of not very much engineering. It's not clear to, in order to go beyond personalized models from the maintenance component, which is honestly the more interesting research sort of avenue for this, it's, before I sort of branched out from that, I'm sort of in search of a compelling reason to do that, but I am looking for those. Does that answer your question?
Yeah, I think so. Okay, and the second question was, may have been already addressed. How do you account for changes in like feature mapping? Like if you have a feature, how long ago the user logged in, and let's say you want to make it like fit to a distribution or something like that. Like do you have to retrain both models, or
Good.
Or like if you have features that are really really sparse, like the unique ID of this song or an ad or something, like how do you account for that?
That's a good question. So the first part, if the feature mapping changes, then so when we retrain so if we change the featurization, then we're going to want to retrain the user models as well. So the way I've been sort of thinking about this and explaining this is we have this sort of dependency pipeline where the user models are dependent on the feature models. So if we change the feature models, we need to retrain everything sort of down the pipeline. We can do all of that in Spark, in this batch process at once, and we can switch over to both of them. So yeah, it doesn't really make sense to sort of update the two independently, but the important thing here is that we can update the user models without having to update the features. For the second case, there's sort of standard machine learning techniques to account for things like the presence of a new sparse feature and things like that. And my understanding is those are primarily domain specific, but you can do things like assume it's 0 or append zeros or things like that, or append ones. Yeah.
Okay.
Yeah.
So to use your example with Catify, suppose you have a cat who does very religiously supply ratings, and another who is very predictable, and the inverse of those as well. Does Velox provide an API for accessing diagnostics for the personal user models? So you could like say, oh, I don't know if we can really make as good a suggestion to this person, so we'll mix it up with more random things.
That's a really interesting idea. So short answer, no, we don't right now. But as part of this sort of evaluation, I am interested in things like clustering based on various criteria, and potentially an interesting one would be amount of training data. I don't know if there's work in the, well, actually, so I mentioned this active learning thing. So I actually used to have on my slides, and then I took it out because I presented this to a variety of audiences, and not everyone gets it. You guys might have appreciated it. But sort of the next step up from this Epsilon greedy thing where you sort of serve randomly, so you can actually look at the uncertainty in your predictions. So you can use like you can have basically like a Bayesian prior or something that can model not just the predicted score, so you're modeling the predicted score, and then you're also modeling the uncertainty about it. And the way, this is called like LinUCB, this upper confidence bound algorithm, and here what we do is we sort of the optimization criteria for this active learning algorithm is to reduce the uncertainty in your model. So then you can do things like do more exploration for users you're really uncertain about, and do much less exploration for users that you have a lot more confidence in.
Cool.
I can point you to a paper if you want as well. Yeah?
For some of these papers that you mentioned in the talk, do you have a link or a list?
So I can put my slides online, and I'm happy to, I don't have a link to like my ongoing bibliography. I can provide it though, it's on my computer. But if anyone's curious, I'm happy to, I'm also happy to like send you an email tomorrow or tonight with some of the papers I mentioned that you can forward as well. Yeah. All right. Oh, yeah, go ahead.
How do you solve the cold start problem?
Oh, that's a great question. So right now the idea is that we pick sort of not the average user model, but the user model that would basically maximize our accuracy across all of the existing ratings that we have. So it's sort of an average, and then go from there. There's also interesting questions with the cold start about, it doesn't make sense to train a user model when we only have 3 interactions, for example. But maybe it makes sense at 10 or 100 or something. So we don't have a great solution right now, but there are standard techniques in the literature to handle this, and we're planning on starting with those until we run into reasons why they don't work. But that's actually one of the sort of the bigger things that I'm concerned about. I'm curious, do you guys have a big problem with sort of the cold start problem?
So I mean, in retail, right? I mean, your catalog changes every day.
Mm-hmm.
You introducing new products.
Yeah.
How do you find recommendation for those products?
Yeah. Yeah. So I was talking about the cold start problem from the user perspective. From the product perspective, that's interesting. I can imagine some ways to do it, like having some sort of similarity measures or things like that. But presumably, if you're introducing a new product to all your customers, you have some reason to believe that it's going to perform well. You have some reason to have bought that or put resources into that. So maybe there's a way to quantify that decision-making process into some initial recommendations. You could also do sort of the Amazon.com approach of blast it on your front page to everyone and get some initial feedback that way.
That could just be included in your base data set.
Right, exactly,
Those
exactly.
are part of your assumptions of your base data set.
I mean, one of the things we want to make sure that we provide enough information to the front-end system so that these predictions and things like that can be sort of filtered through any non-statistical business logic or application logic that needs to be dealt with. Yeah.
Well, I mean, I kind of have a partial suggestions to the cold start problem, and also comes to the question for you. So let's say, like, if you got a new user, don't know like user's history, but if your data science team said that, like, hey, we can actually predict from social networking because maybe you like what your friends like. So if your social network, we can just incorporate that. How would I actually incorporate that kind of new feature into your system? Like,
so in some sense, that's a very hot topic of research right now. So there's a few things. I actually read an article earlier today about this idea of cross-domain recommender systems, where if I know you like this movie, I can recommend not just other movies you like, but also maybe books or music or things like that. And I see that as sort of a complementary problem to what you're saying. These collaborative filtering models are, in some sense, a way of getting at that, where if I like things that a bunch of other users have liked, then my model is going to recommend other things that they liked. So you can think of it as a sort of bipartite graph between my items and my users, and I want things that are tightly connected. Alternatively, you could come up with some model that takes in this Facebook information and says something about the type of user you are, for example, or I don't know, take sort of a more domain-specific approach to it as well. But I guess I want to pop up a little bit and say that the hope is that we give you a wide array of ways to express features, and then you figure out what the right ones are, and once you tell us what the features are, we're going to help you deploy them. But I make no claims that we're going to make it easier to develop these models, and all of these predictions and things like that are only going to be as good as the models and the training data that you have. And we're interested in helping facilitate you gather more and better training data and things like that, but ultimately if you have crappy data scientists and poor models or not enough data, or a really hard domain, we're not going to help you. All right, thank you all. I'll stick around for another few minutes if anyone wants to talk to me as well.